Welcome to this lecture on moisture balance in building physics. Today, we compare two very different buildings, a newly constructed studio apartment and a converted basement flat. Both have residents. Both have heating. But only one of them has a serious mold problem. By the end of this video, you will know exactly why and be able to predict it using mathematics. On the left, we have the studio apartment, 75 cubic meters, heated to 21 degrees Celsius, cast in situ concrete walls with a large glass window. The resident has no major complaints. On the right, the basement flat, 96 cubic meters, heated to 20 degrees, but constructed below ground level with no damp-proof membrane in the floor slab. The resident notices mold patches near the floor and a persistent damp smell, despite keeping the heating on. Our task is to calculate the steady-state indoor relative humidity for each building using the four-step moisture balance method, and then compare the results to explain why the basement is at risk and the apartment is not. Before we calculate anything, we must identify all moisture sources for each building. We follow section 3.1 of the DTU Building Physics Framework, which defines four categories of moisture input. The first source is built-in moisture. In the apartment, the freshly cast concrete releases 20 grams per hour as it cures. In the basement, moisture rises from the ground through the unprotected slab at 35 grams per hour, nearly double, and it will not stop once curing is complete. The internal occupant load. The apartment has one resident whose cooking, breathing, and laundry contribute 120 grams per hour. The basement has two occupants, plus a shower used daily indoors, raising the total to 150 grams per hour. The external boundary condition. The apartment faces cold winter air at -2 degrees and 90% humidity. This air is actually quite dry in absolute terms because it is so cold. The basement, however, faces milder outdoor air at +5 degrees and 85% humidity. Warmer air holds significantly more moisture, so the incoming ventilation air itself carries more water vapor. Finally, ventilation. The apartment's exhaust fan provides 0.5 air changes per hour, 45 kilograms of air per hour, which is a reasonable rate. The basement has only trickle vents providing 0.3 air changes per hour, or 34.6 kilograms per hour. This lower ventilation rate is critical. It means moisture generated indoors is removed more slowly. With all four sources identified for both buildings, we can now begin the quantitative calculation. We will work through each of the four steps for both buildings simultaneously, so you can see exactly where the difference arises. Step 1. External vapor state. We calculate the actual outdoor vapor pressure for each set of outdoor conditions using the empirical formula where saturation pressure equals 288.68 times 1.098 plus T over 100, all raised to the power of 8.02. For the apartment, we substitute -2 degrees Celsius into the empirical formula. P added -2 equals 288.68 times 1.078 raised to the power of 8.02. Giving approximately 517 pascals. Multiplying by the relative humidity of 90% gives an actual outdoor vapor pressure of 465 pascals. For the basement, the outdoor temperature is +5 degrees Celsius, warmer than the apartment's outdoor conditions. P at 5 degrees equals 288.68 times 1.148 to the power of 8.02, giving 872 pascals. At 85% relative humidity, the actual outdoor vapor pressure is 741 pascals, 60% higher than the apartment. This means the ventilation air entering the basement is already carrying significantly more moisture. The external vapor pressures are now established. Apartment, 465 pascals. Basement, 741 pascals. We proceed to step 2. Step 2. Total moisture generation. We sum the internal sources for each building. For the apartment, G total equals 20 grams per hour from curing concrete plus 120 grams per hour from occupant loads, giving a total generation rate of 140 grams per hour or 0.14 kilograms per hour. For the basement, G total equals 35 grams per hour from rising damp plus 150 grams per hour from the two occupants and shower, totaling 185 grams per hour or 0.185 kilograms per hour. The basement generates 32% more moisture internally. Combined with lower ventilation, this is already a concerning pattern. G total established. Apartment, 0.14 kilograms per hour. Basement, 0.185 kilograms per hour. Proceeding to Step 3. Step 3. We now apply the steady-state mass balance equation to find the indoor-specific humidity for each building. The governing equation is the same for both buildings, Xi equals Xe, plus G total divided by Ga. The outdoor-specific humidity Xe depends on the outdoor conditions of each building, and the ratio G total over Ga reflects the balance between moisture generation and ventilation capacity. For the apartment, the outdoor vapor density ρV equals 465 divided by 462 times 271.15, giving 0.0037 kilograms per cubic meter. The outdoor specific humidity Xe is 0.0037 divided by 1.2, giving 0.0031 kilograms per kilogram. Substituting into the mass balance, Xi equals 0.0031 plus 0.14 divided by 45, giving an indoor-specific humidity of 0.0062 kilograms per kilogram. For the basement, at the warmer outdoor temperature of 5 degrees, ρV equals 741 divided by 462 times 278.15, giving 0.00577 kilograms per cubic meter. Xe is 0.00577 divided by 1.2, equal to 0.00481 kilograms per kilogram. Substituting, Xi equals 0.00481 plus 0.185 divided by 34.6, giving an indoor-specific humidity of 0.01016 kilograms per kilogram. This is over 60% higher than the apartment, a combination of wetter incoming air and more internal generation and less ventilation. Indoor-specific humidity established. Apartment, 0.0062. Basement, 0.0102. The difference is substantial. Now for the final conversion. The final step. We convert each indoor-specific humidity into relative humidity. For the apartment at 21 degrees Celsius, the indoor vapor pressure PVI is approximately 1011 pascals, against a saturation pressure of 2487 pascals at 21 degrees. The indoor relative humidity is 1011 divided by 2487, 41%. This is comfortably within the recommended 40 to 60% range. No mold risk. For the basement at 20 degrees Celsius, the indoor vapor pressure is approximately 1652 pascals, against a saturation pressure of 2437 pascals. The relative humidity is 1652 divided by 2437, 68%. This exceeds the 60% threshold above which mold growth becomes a serious risk on cold surfaces. The calculation confirms what the resident is experiencing. Let us now place both sets of results side by side in a single comparison table. Reading down the table, the apartment faces colder but drier outdoor conditions. Its outdoor vapor pressure is 465 pascals. Total moisture generation is 0.14 kilograms per hour. Ventilation removes 45 kilograms per hour. The result, an indoor-specific humidity of 0.0062, a vapor pressure of 1011 pascals, and a relative humidity of 41%, safe. The basement tells a different story. Warmer but still humid outdoor air brings in more moisture. Higher generation, 0.185 kilograms per hour, combined with lower ventilation, only 34.6 kilograms per hour, pushes the indoor-specific humidity to 0.0102. The indoor vapor pressure reaches 1652 pascals, and the relative humidity is 68%. That is 8 percentage points above the mold growth threshold. Let us visualize the key result. Here is the indoor relative humidity for each building, plotted as a bar chart. The dashed line at 60% marks the mold growth threshold. The contrast is stark. The apartment bar reaches 41%, comfortably below the threshold. The basement bar at 68% clears the threshold by 8 percentage points. This is not a marginal case, it is a building that will grow mold without intervention. Now that we have quantified the problem, what can be done? Let us look at targeted interventions for each building. For the apartment, the situation is already acceptable. The main advice is to monitor indoor humidity during the concrete curing phase, which may last several months. If condensation appears on the windows, this indicates that surface temperatures are dropping below the dew point, and double glazing should be considered. The basement requires immediate action on 3 fronts. First, a damp-proof membrane should be installed in the floor slab. This alone would reduce G-built from 35 grams per hour to near zero, cutting G-total by almost 20%. Second, the ventilation rate must be increased to at least 0.5 air changes per hour. Even without the membrane, this alone would bring the indoor RH down by approximately 8 percentage points. Third, a mechanical dehumidifier provides direct control and is particularly useful during periods of high occupant activity such as cooking and showering. The key engineering insight from this comparison is this: the indoor relative humidity is controlled by 3 levers. The total moisture generation rate G-total, the ventilation air mass flow rate Ga, and the outdoor conditions, which set the baseline Xe. When all 3 are unfavorable simultaneously, as in the basement, the risk compounds rapidly. The mass balance equation makes this visible and quantifiable. In the next lecture, we will extend this analysis to assess condensation risk on specific building envelope elements using the dew point criterion. We will show how to identify which surface in the basement is most at risk, and by how many degrees its temperature must be raised to eliminate condensation. Thank you for watching. If you found this helpful, please subscribe and leave a comment with any questions.